Hello and welcome to our 16-831 final presentation. I'm Philip Bailey. I'm joined by Dale McConachie and Haley Dalzell. Our project is Filterception, the Ded Reckoning. The problem we are trying to solve is that different localization filters have their own strengths and weaknesses. For instance, the particle filter could get lost. It could converge to an incorrect location, or just take a long time for a particle to end up in the right location for the whole filter to converge. On the other hand, the common filter can get too confident in one incorrect location and then ignore correcting sensor data and just stay in that location. Or you could get a GPS multipath-like situation where a common filter sees an unlikely reading and thinks that the robot must have suddenly moved very far. These are things that we'd really like to mitigate with this project.
Our concept is to use multiple filters in parallel and fuse the results to create a more accurate position estimate. The idea is to use the strengths of one filter to mitigate the weaknesses of another. This way, if one fails, the others can correct it. By using filters with different failure modes, we can lower the chance of a complete system failure. Here we show the overall system architecture. We chose to use a particle filter and a Kalman filter for our implementation. However, any type and number of filters could theoretically be used. These subfilters take in sensor information and provide a state estimate to the Kalman filter overlord. The overlord merges these estimates and provides feedback to the subfilters.
For our data, we use the MIT DARPA Urban Grand Challenge Open Dataset. From that, we used the Applanix Sensor Suite output as the input to our filters. We initially wanted to use GPS as the input, but we had a hard time finding a ground truth for that. So instead, for ground truth, we used the Applanix pose estimate. Then, for the data that we then put into the filters, we used the Applanix pose and then added noise. For the motion data, we then took the Applanix velocity estimate. This allowed all of our data to be consistent and then our model to be testable and easily evaluated. For the constituent filters for our overlord, we used a Kalman filter and a particle filter. The Kalman filter was a very standard Kalman filter that uses position and velocity in its motion model in order to predict the next location. It ignores feedback from the overlord and returns its pose based on only its internal state. The particle filter is also a standard particle filter. It returns pose based on a weighted average of all the particles, weighted by their probabilities. The way our particle filter differs, however, is that it uses feedback from the overlord to place new particles in likely locations. In these locations, future sensor updates should be more likely, and thus these particles should spawn more particles there and the particle filter will start tracking correctly.
The overlord filter's position estimate is a weighted average of all subfilter position estimates. These weights are based on the confidence of each subfilter in its estimate. The overlord filter uses a Kalman filter to keep track of the variance of position estimates and confidence of each subfilter. The confidences are used to determine a position estimate, as described above. The variances show overall filter performance. Ideally, the X, Y, and Z variance of all the filters should decrease over time.
We tested two versions of our algorithm in order to evaluate the overall performance. First, we tested the system without any feedback loop. This enabled us to evaluate the performance of the constituent filters as well as determine how the overlord was responding to the confidences that each of them reported. As you can see, the particle filter took a long time to converge, while the Kalman filter was able to accurately track the GPS right from the start. As the particle filter converged, its confidence increased and the overlord began to trust it more and more, resulting in the overlord actually drifting away from the true position of the robot. That said, we can see that the overall performance of the overlord is much better than the particle filter by itself, which is what we were looking for. Once we added the feedback loop, we can see that the particle filter converged very quickly and actually outperformed the Kalman filter at the start of the trial. As a result of the particle filter and Kalman filter both having accurate estimates, the overlord is able to provide its own estimate, which outperforms the previous results without feedback. As time passes, we can see that the Kalman filter actually degrades its performance while the particle filter improves. We can see at 2.5 seconds a spike in the error of the Kalman filter, while both the overlord and the particle filter still do well. As more time passes, we see that the particle filter actually loses track slightly, while the Kalman filter improves. The overlord is able to intelligently average these two results and come up with an estimate that is once again better than the particle filter could do by itself. So as we can see, with or without feedback, the overlord performs better than the worst filter. This enables us to trade off a little bit of error at all times to prevent catastrophic failures in the long term. The worst failure modes of the constituent filters are mitigated while taking advantage of the benefits of each individually. Overall, Filterception worked very well and is general enough to be able to apply to many different application areas.